So I'll be talking about what we've been doing on Smøla at the wind power plant at Smøla, but I'll mainly focus on options for mitigation. So in Norway, we have kind of a certain amount of installed capacity. Not a lot yet compared to many other countries, but still there's quite a lot kind of spread throughout the coastal areas, mainly in Norway. And as you can see by the arrow, that is where we find the island of Smøla with its power plant there. And this power plant, where we've done most of our research, consists of 68 2-megawatt turbines. But at the same time, when it is also a very good site for production of wind energy, it's also kind of a very varied archipelago with kind of one main island and a lot of many over 5,000 islets and skerries that are around it. And because of that, it's also a very bird-rich area with, among others, also 60 Whitehill Eagle territories. So when we started doing our research, what we also found after it was built, that there was actually there was some species that were affected by this. And especially two species kind of were mainly or are still mainly affected, which is the willow ptarmigan, which we suspect to actually collide with the turbine towers, and the white-tailed eagle. So this is also kind of triggered kind of much of our research, and since 2006 we have now done quite a lot of research, mostly connected to two large research projects. One called Birdwind, that was more on focusing on trying to understand the conflict and the extent of the conflict, and thereafter the Intact project, where we specifically wanted to look at possible solutions to that problem and trying to find test those measures or different measures. So what have we found, especially in the first projects with regard to white-tailed eagles? We found some behavioral responses where we looked at both using GPS collars, using visual observations, and also using regular monitoring, is that there was a displacement that we found by approximately 40% reduced use of the wind power plant area. However, if you look at their behavior, their in-flight behavior, that actually there was no change in their behavior if you compare their flight behavior outside and inside the wind power plant, which is kind of dangerous to do that, or not to have any avoidance behaviors. But looking at how many birds actually collided versus how many were expected to collide if they have really no avoidance, then still they did escape collision. So maybe at a very fine scale. If you look at collision risk, then it's very clearly site-specific and seasonal specific, with main peaks in spring when adults start to establish their home ranges for the summer for the breeding. And late summer when they the young leave the nest, and territories are becoming more open and less guarded compared to summer and spring. There's also an effect of distance to and a density of nest sites, both inside and surrounding the wind power plants, and also local terrain conditions, and also the where the turbines are and the end of row turbines. This obviously can also have an effect at a larger scale. And what we see also, that if we look at the population level, that we see that there's, looking at the mortality, so those species that actually collide, that is both local eagles, which should have been adapted and known with the situation, but also you could say naive eagles that are not locally from the local population. And this we looked at using DNA techniques to find out if they were from known nest sites or not. And it's both adults and subadults that get killed. And this in turn also led to a reduction in the reproductive success within the area and close to the area of the wind power plant, because loss of adults also will have an effect on the reproduction. And in all that reduced survival within a 5-kilometer range around the wind power plant, and looking at the total population growth rate, that was negative within a 1-kilometer range of the wind power plant. So locally, that has a negative effect. But if you take into account a larger area around the wind power plant and kind of include more nest sites and a larger proportion of the local population, that effect is lost. So it has a very localized effect on the population. So what can you do about that? Now we know kind of what the problem is, but how do you solve that? And I think it's very important to kind of look at this kind of the mitigation hierarchy, to use that at all times. And they are, I think, very strictly connected to different, you could say, decision gates, kind of when decisions are made during the lifetime of a wind power plant. First, you try and need to avoid areas, choosing areas to plan for a wind power plant at an early stage. But once you've made that decision and have chosen your site where to go and construct a wind power plant, you cannot avoid anymore, but you can minimize. You kind of, for example, the placement of the turbines, etc. So the design of the actual wind power plant. Once you've done that and the design is done and you start constructing, you don't have that option anymore, but you still can reduce in using different measures, which preferably are done during construction, because then they're operational when you start operating the wind power plant. And then during operation, all the other things have been implemented, and then the only thing that is left is really to compensate anything which is still kind of a residual impact, either monetary or non-monetary. And finally, during decommissioning, you have to restore the area. If not, you're going to have this kind of feedback loop when you are choosing to repower, and then you can go back to the design phase and kind of improve the design, given that also you may have had and have obtained new knowledge. So I'll give you some examples of what we've been working on within these different blocks in a way. So starting with the avoid action, we developed a tool called Consite Wind Toolbox. Consite stands for consensus-based siting. And what it does, it's a multi-criteria decision support system that tries and find, optimal siting or best kind of best practice siting of wind power plants based on both ecological criteria, societal criteria, and technological criteria, which are all important. If you can identify all those criteria and map them, you can put them all together and to create kind of a conflict map, what we call it, on the left, seen on the left hand side. And thereafter, you can look at that conflict map and offset that at the production potential across the landscape. And from that, kind of identify, optimal sites, which are depicted in the middle one. Given a certain size that you want to have, so that at least there's room for a certain amount of turbines, depending on kind of how large of an area you wish to develop. But once you've done that, you can see also not only kind of what are the best sites, and here in this case, there's just 3 stars in between. There's actually sites that are being constructed at the moment. So actually kind of it shows that our model kind of can identify suitable sites, which are also kind of independently of this tool, were also chosen to develop anyway. But it makes it more transparent now, because now you can actually look at the entire site or at specific turbines in that site and get a list. Not readable, but it's you get a list of all the different criteria and the level of conflict. So you can actually see, okay, is this acceptable for all the different criteria that are added? If it's not acceptable, can I mitigate that somehow? Can I choose to avoid it locally, or can I kind of in a design phase, or can I do some mitigation measures to reduce it? And the choices you made and what the consequences of those choices were. So that may help in kind of avoiding sites that have too high levels of conflict. Now, once you've decided on the area, what can you do? We have looked at it also from a point of view of micrositing of turbines. And one thing we know that especially soaring birds, raptors, but also storks, etc., are using updrafts, so kind of vertical wind speeds, either created through thermal warming of the terrain, or because of upwards pressure of air due to topography, are attracted to such sites. And often also such sites may also be where you have wind turbines. So what we wanted to do is to map that in the landscape. We're now building kind of a tool in Google Earth Engine. So in the end, it should be possible to run this globally for any given site of interest, where you can choose kind of the date you're interested in and a certain species you're interested in, and you can map it in the landscape. And where do I have high levels of updraft speeds, which also gives you an increased risk. And here it shows also for the island of Smøla, which is the one down to the left, where you have very little topography, and therefore the orographic, so the updraft due to topography, is no problem. So you have a slight problem still of thermal updrafts, but not the orographic uplift. On the neighboring islands of Hitra, for example, on the right, you can see that locally it does have an effect. You can see that there are some areas where you have to take into account much more. So that can help also kind of in siting turbines. Okay, once we've started to construct the different turbines, what can we do? We tested various measures that you can help reduce it. One is, and I think that's mentioned kind of many times now lately, is painting of turbines. So what we tried was to paint one of three blades black. And the idea is that that will make the blades more visible. Not only more visible in itself that it has a kind of different color, but also to reduce so-called motion smear. You have to remember that, especially at the tip, the rotor blades can turn quite fast, up to 250 kilometers an hour, which makes them blurred. Now, laboratory studies have shown that if you paint one of three blades black, this motion smear is reduced. So this was kind of our approach, kind of to test this, kind of, is this true? Does it help at all? And in all, we looked at both their behavior. We found very minor changes, so not very clear effects of their behavior, but collision rates decreased by over 70%. So quite a large effect. So I think this is kind of very successful, but of course, every study has its limitation. This is one study. It worked apparently at Smøla, but now it would be good to replicate it in other places to see if it also works in other situations. The other one is the painting of the turbine tower. As I said in the start, we have kind of the willow ptarmigan that we think collide with the tower. So what we did was to paint the lower 10 meters black to kind of increase the horizon. So it looks like a kind of a higher area in the landscape, which makes it easier for them to avoid it. Now, what we saw also there, kind of collision rates dropped by over 50%. With the highest effects in spring and autumn. So yes, it seems to have some effect there, and that's also merits kind of further research in that sense for that kind of species. But one thing to kind of remember when you kind of start painting is that we were doing it after the wind power plant already was operational, which meant we had to have people kind of in lifts kind of going up and down a blade, which is not very easy. And that also shows that if you would be able to do it during construction or even in a factory, this painting job would be much easier in a way. So, that's something to consider. And obviously another matter that you have to consider is that, well, visual effects. I've shown show here some pictures also kind of a bit from a distance, kind of how it looks like. Yes, it's visible. If you have people living very close by, they may see it. But if you're at a kind of bit farther distance, that it's not that visible. And I find it personally that actually the painted towers are more visible than the blades. And I think that's because of their kind of the shape in a way, in how they look like. And of course, you need to have an option to be allowed to paint, to get exemption from the regulations for white, grayish paint, both from the consenting authority and the aviation authorities. So that's something to keep in mind. We also tested the potential efficacy of using ultraviolet, and we call it kind of a light fence at that time, to see if that ultraviolet light would deter birds from an area. We did a pilot for that, putting the ultraviolet lights pointing upwards and monitor the area with a bird radar. especially during reduced visual conditions, so during the night. And yes, we found a reduction by 10, 20, 30%, and that the birds flew 7 meters higher than on nights without the lights. However, if you consider that a blade has a 40, 50, even kind of longer length, then 70 meters is far from enough. And that would mean I would have to use much stronger lights or some other design. But you have to remember that also, one, not all species are able to see ultraviolet light. So what is your species of interest? That is something that has to be kept in mind. And two, these lights have also a safety distance. So you have to take care of that and not blinding animals.
Okay. Mr. May I ask you to keep in time, please?
Yeah, I'll try that. Yeah.
Kind of finished with the time. Yeah. Thank you.
Very short and operational adjustments. I think there's other people coming into that where you can actually look at the reduction versus production and kind of find optimal reductions there in that sense. Compensate and restore. This is very short. Basically, there's unknown options. I think we need much more knowledge on that, kind of what are the options and possibilities for doing that in the future. And we can learn much more. Once we have more data, we can also kind of get more environmentally friendly designs in the future. And finally, my final slide here is that I think it's also very important that if you start doing mitigation, you have to kind of always keep in mind that it's a trade-off between what society wants, the technology that we have, and also kind of taking into account how to reduce impacts on the environment. So having that kind of balanced design and involving all beneficiaries, both for the development and the mitigation, to get a kind of adaptive and integrated design to mitigation. So that's balancing all those multiple interests. So that was it. Thank you.